Hello, everyone. Welcome to another LoRa Alliance technical webinar. Thank you so much for being here with us today. We're going to just give it another few seconds to let everyone get connected, but we are going to get started on time here, as we do have a lot of great information for you today. So we'll just give it another few seconds, and we'll go ahead and get started. Alrighty. Hi, everyone. I'm Megan Leonard, Global Program Manager for the LoRa Alliance, and thank you for joining our LoRa Alliance webinar today, which we are focusing on LoRaWAN Payload Codec API, so another great webinar in our technical series. Before we get started, just a couple quick notes for you all. If you're having any technical issues during this webinar, usually refreshing your screen, which you can do so by pressing F5 on your keyboard, typically solves any technical issues you might be having. There's also a help menu bar at the bottom of your screen, and you will see a help box within that menu bar. So that's also a great resource if you're having any issues during today's webinar. The other important box on your screen is the box labeled Q&A. So if you have any questions for our presenter throughout the webinar, you can go ahead and just type in your questions into that Q&A box and press submit, and we'll receive the question on the back end here, and then we'll answer all of those questions at the end of today's webinar. So please be utilizing it any time throughout today's webinar to just type your question in and submit it to our speaker. Lastly, just a reminder that these webinars are available on demand after today's webinars. So it's about 24 hours and then it becomes available on demand, and you can access the on-demand version using the same link you used to join today's webinar. So with that, I want to get into today's topic. Our speaker, Mostafa, is from one of our LoRa Alliance member companies, Actility. And he's also the chair of the Payload Codec API Task Force within the LoRa Alliance. So I'm just going to go ahead and hand over to him now. And so take it away, Mustafa.
So thank you, Megan, for the notes and the introduction. And hello, everyone. Before starting, I would like to thank you all for joining and attending a new technical webinar from LoRa Alliance. So as mentioned, Megan, I'm Mustafa Ibrahim, a software development engineer at Actility, which is a member of LoRa Alliance, and the chair of the task force of Payload Codec API, which will be presented in this webinar. Let's start from an outline of what the webinar will contain today. So this is an outline starting from a small introduction to briefly present an overview of the topic, to be more familiar with what we will present, then presenting what's the problem in the current use of codecs, and the proposed and provided solution by the technical committee under LoRa Alliance. To be more clear for attendees, we will go through some points to learn more about the API structure, the metadata, the requirements and recommendations when following this standard, which are more explained in details in the specification published by the LoRa Alliance. And you will all have access and reference link to the specification at the end of this webinar. Let's start from the introduction. For the communication between any LoRaWAN device and application server normally must be translated. So must be translated, and the codec itself, it's the piece of code which is responsible to translate it or to decode an uplink, downlink, and to encode downlinks also for a device or a group of devices. So to clarify more what's an uplink, what's a downlink, and why a codec is needed, because the data to be transmitted by LoRaWAN devices or applications normally send as an encrypted data or send as just some bytes. So it needs to be decoded to be more useful on the server, or even to a human to be readable in a readable format for the server or human. And the same process is also needed when a human or server needs to configure some device, to communicate with the device and configure it in a way or another. So these data must be also translated, and we said encoded to a binary format. As each device has its specification and its technical characteristics in terms of hardware or any other specification, each device has its own way of communication in a chain of bytes. Then that's why each device normally needs a dedicated codec to do the translation process. So why this the current use, why now this one-to-one relationship between the device, the LoRaWAN device and the codec is not optimal, or it needs some structuring. Let's see. This is the problem now. So starting from describing the process currently to conclude the problem. So in the encoding and decoding process of application payloads, and here we mean by payload, it's and here in the next slides we mean by payloads, the data communicated between device and application server in the two ways. So each time a device application is introduced or modified, so introduced with its specific rules, its specific characteristics, or modified, we mean updated in a way with no backward compatibility. So there's two ways to support this device when in that case. Either the application server vendors need to develop a codec for this device, or the device maker need to develop a codec for each application server vendor already exists on the LoRaWAN community. And another case also, each time a new application server is introduced, there's two ways to support this the codecs. Either the application server vendor develop the codec for all the existing devices according to its API, its own API, or each device maker must develop a codec for this new application server vendor. And this really creates a huge friction for the onboarding devices and application server platforms. Let's just go through a simple example. And it's really simple, as we have here in this example, three application servers. And each application server has its own API. You can see API X, Y, and Z, and its own way of writing decoders. And we have also three device makers, A, B, and C. Assuming that each device maker has one device, so he first needs to create a codec or implement a codec following the API of each application server. So he needs to implement three codecs, one per API, per application server. And the same process must be done from the device maker B. For one device, he needs to create three codecs. And the device maker C, the same process. Here is an overview of the whole of the whole case here in the case of three application servers, three device maker with one device. So it's really a small example. It's a simple example that shows only three devices and only three servers in the field. You can imagine how the complexity would be strongly increased in case of massive LoRaWAN deployments. And the real case is really not this one. There's much more than that as application servers and device makers. Adding to that, here we are assuming that each device maker has one device, and also this is not the real case in the real life, because each device maker normally manufactures at least a minimum of 3 to 4 devices, and some will have more than 20. So the complexity will be huge on the ecosystem. What's the solution provided by the LoRa Alliance Technical Committee? We have said that in order to face the time and effort complexity, the LoRa Alliance defines a standard codec API that can be adopted by both the device makers and application servers, which was the goal of this specification. So why we are proposing to standardize the codec? Because when we have now, if we take the case of the problem, we take it when we have any application server, a new application server or a device maker. So the device maker must develop the codec implementation only one time, and thus it will be compatible with all the servers that follow the LoRa Alliance standard codec API, and this allows to easily integrate any LoRa Alliance device into the compatible platforms that uses this standard. So let's go back to the same example that we have taken before, but now you can see that all the application servers, for example, use the same API, which is the standard API that we are providing here in the specification. And also the device makers, A, B, and C, each one has one device, only one device. So before that was the case. Each device maker want to create three or implement three codecs for all servers. But now, instead of having API X, Y, and Z, the device maker A will have to implement only one codec, and it will be compatible with all the servers. And the same for device maker B, device maker C. And I will repeat one more time, this is just a simple example. It shows a very simplified case. As much as the number of devices and application servers that are compatible with LoRaWAN increases, as this standardization would simplify the process and reduce the complexity, and would have an effect on reducing the complexity and friction while onboarding new devices or even new application servers. So now, as we know about the advantages of this standard, let's go through its structure, how it will be implemented, the metadata and requirements recommendation, as we said. Here's a slide that shows, in fact, the API structure, the API, the LoRaWAN Payload Codec API doesn't just it's not just trying to standardize the code, the code that will be interpreted, but even the metadata, which the information used for identifying the codec itself, the vendor of the device, the version, and etc. So and the JavaScript code for sure. The programming language chosen in this codec was JavaScript because it's really lightweight, interpreted, and can be compiled just in time with first-class functions. There's more information, details about that in the specification as we chose the JavaScript ES5 as it's simple and widely supported in most communities and interpreted by most browsers. So in this section, we'll describe the three JavaScript functions that the codec may declare to perform encoding, decoding tasks. Here in red, we have the decode uplink, which is the mandatory function that without this function, a codec cannot be valid. And the encode downlink, decode downlink are optional and are only mandatory when the device supports downlink. So every codec function between these three is defined by its name, input and output. In all cases, the input and output are JavaScript objects. This to allow, let's say, future evolution of this API. If you want to add some more fields in the input and the output, some more properties, this will not create any breaking change. So let's go start by the uplink decode function signature. Each function, as we said, is described by its input and output. The input and output are JavaScript objects, and inside there are three properties for decode uplink. bytes, F port, and receive time. So the bytes is an array. All these three are mandatory to decode an uplink. A bytes is an array of bytes, which is the payload to be decoded, the payload sent by the device to the application server to be decoded to a human-readable format, where a byte is represented with an integer between 0 and 255. The F port, which is the port field, this one is always also mandatory. Normally, there is some limited ranges for not to be used as F port. Others can be used freely for any purpose. For example, to specify the type of message that's sent from the device. And you can find on the LoRa Alliance site the limitations on using which numbers of F port. The receive time, which is the uplink message time, it's normally a JavaScript date object, and this is also mandatory. In the output object, we have data, errors, and warnings. Actually, when the decoding process done correctly, successfully, the data will be mandatory because it's the decoded payload, and it's really an open JavaScript object. So you can see, for example, in the example here, it's temperature 41. You can have anything inside this object data. Depends on the device specification and what the device can be used to. Errors, this one is mandatory. Is mandatory only when failed, and we said failed. A failure means that the provided payload cannot be decoded, or by some reason, why cannot be decoded? By some reason, the data were wrongly arrived to the codec, either according to an issue in the device or to an issue of communication between the device and the application servers. So it's a list of text, simple text, describing the errors that has been happened during the decoding process. And when the errors will be there, the data object will disappear because the data cannot be decoded. So this is optional and mandatory only if failed. Warnings is an optional, always an optional field or property, and it gives a list of warnings for some issues maybe happened during the decoding process, but didn't prevent the codec from giving an output. Even if it can be used for an alert, for example, and this is the example. So you can see that the input is the bytes encoded, which is encrypted, and the F port and the time. Then these, according to some specification of the device, we have created the codec with a decode uplink that will be decoded to say that the temperature now is 41 to send it to the application server. And you can see the warning here is used as an alert. So nothing, the data already decoded, nothing wrong, but there is an alert that the temperature exceeds 40 degrees. That depends on the device. So the downlink encode function signature, in the downlink, it's reversed. So we are sending data from the server to the device to configure it, for example. So as we already mentioned, contrary to the decode uplink function, the implementation of this function is only mandatory when a device supports downlinks. So for sure, the data and the input always mandatory as it's the only source of configuration or of information to be sent to device. And in output, there is bytes, F port, errors, warnings. Bytes, which is an array of encoded data represented by bytes, again, an integer between 0 and 255. And this is only mandatory when success. And the F port will be also mandatory with it. There is errors, and this one is mandatory only when failed. So as we have already mentioned in the decode uplink, if the decoder for some reason fails to encode some data, it will give a list of errors to the user, to the developer, to the application server. Depends. And the warnings, the list of alerts, list of errors that didn't prevent the codec from encoding the payload. Here's an example. So here we are saying that we need to set the temperature threshold to 40. The encode downlink will encode this to be understood by the device. So it sends just an array of bytes and on this F port. And the device will be manufactured in a way that if I receive these bytes and this F port, then I have to configure this part of hardware. Then the last function will be the downlink decode. You may ask why we have to decode the downlink as we are already encoding it. We need just to send data from application server to device. But this is an optional function, but it may present when device also support downlink, but also it makes it easier to monitor what's happening, what we are sending from the application server side, monitor the logs, for example, statistics on the downlink that has been sent to the device. So it will, it's the inverse of that one. So that one was the encoding. Here it's the decoding of the downlink, the bytes that must be sent to the device, the F port, and the receive time. So, and this is these are also already explained in previous slides. And the output will be data, the data that I have to send to device to set this threshold. So you can see the errors and warnings also. You can see here's the decode downlink. If I send this one 16 with an F port 16, it will say that I have to set temperature threshold to 40 in order to receive this one on the device side. This is really, if you compare these two examples, it's the inverse. So here we have sending this one, we have received the one that will be sent to device, and here's the decode of the downlink, and this is useful only for monitoring the logs or anything. Going back to this slide, we said that the API is not only standardizing the code, the JavaScript code, but also the metadata. So what's the metadata? The codec metadata includes the main file that has some properties, some fields of information that are needed to identify the codec, and some also additional metadata as examples and data description that are recommended. So what's the main file? Actually, it's a JSON file, and it has the information that help using the codec with different runtime environment. This one must be delivered alongside the JavaScript code to simplify the distribution and integration of the codec with any LoRaWAN platform compatible with this standard API. So what's inside this file, this JSON file? There is some fields, and most of them are important for sure. The codec ID, it's an identifier that defined by codec developer, but it's unique. It's 4 hexadecimal characters and it's unique. So we will have on the LoRa Alliance side a list of all the codec IDs in order to identify any codec with its ID directly. As we have already for the vendor IDs, for example, any vendor that's a member of LoRa Alliance, he has an ID, a unique ID on the LoRa Alliance side, and it's listed on our side. The source URL, its URL refers to the source of the code. It might be a GitHub repo, a URL to GitHub repository, a URL to the website of the company that manufactured this device or that created this codec. It depends. Vendor ID, the identifier given to the vendor by the LoRa Alliance, it's also 4 hexadecimal characters, and there's already some there are already some vendors that that has IDs on the LoRa Alliance. So all the members, the vendors that are members, having already an ID. The MAC, it's the IEEE MAC block. This one is only mandatory if there is no vendor ID. So the MAC used as an alternative of the vendor IDs, because if a vendor of device needs to use this specification, this standardization, in order to ease the use of his codec on all the LoRaWAN platforms, and he is not a member of LoRa Alliance, he will not have a vendor ID, so he can use the MAC instead. The version, and it's the version of the codec, because it follows the semantic versioning, and normally this is important because if in the future the codec must be maintained, or even the device has been modified, the codec must be updated. So the version is really important to be used in the metadata. The main property, it refers to the file that has the three main functions: decode uplink, decode downlink, encode downlink in the codec. So it refers just a reference to where these, what's the name of the file that's delivered with this JSON file that has the code. Spec version is the version of the spec followed when creating the codec. Now we have only the 1.0.0, the first version of the specification, but maybe in the future we need to add some properties. We need to add to do some modifications on the specification, so the version will be increased, and thus the spec version is really an important field here in order to the application server to know which. For an application server, they can say, okay, we support this version of the spec, the standard codec on this version of the spec, and the codec developer also need to know the spec version that's supported by the application server. Name, this one is an optional one. It's any commercial name for the codec used. It can be used for I don't know, for just a commercial name. A codec, here it's an object. It's just a JavaScript object, and it's optional normally, and not it's mandatory normally, but it describes what's optional functionalities are already supported by this codec. Because as we said, the downlink is not supported by all devices or by all codecs. So here it's a Boolean said, okay, downlink. True, I support downlink in this codec. Examples and JSON schemas we will see in the later slides, later in the next slides. What are the examples and what are the JSON schemas, and these are optional. So in the codec there is a property said if they are supported or not. So also, as we said, there is additional metadata which is optional. In order to help the user of the codec, or even the application server, the developer may provide a list of examples. Examples of what? Examples of the code, of the bytes to be decoded, and what's the expected output normally. These examples will be used by the LoRaWAN platforms to suggest, for example, some payloads to the user when testing the codec. They are also useful to assess the code implementation, codec memory consumption, time execution, to compute the coverage, to give the quality of the codec, or a score of the codec depends on the coverage. So these examples are delivered alongside the metadata with an examples to JSON file. And there's three types of these examples: uplink, downlink encode, downlink decode. The uplink will give an example of the input as a bytes and F port, and the expected output data. The downlink encode, the input will be the data, and the expected output as a bytes array and F port. And the downlink decode, the same as the uplink, as an input it will be bytes and F port, and the output will be data. Another additional metadata will be the data description. The data description, we have already mentioned that the data that will be outputted from a codec, it's really open. It's an open object. So it's a decoded view of payloads in a JavaScript object that's open, which is by construction a JSON object. So there is a direct one-to-one mapping, no problem. But we don't know what's inside. So in order to ease the integration with the platforms, a description of a structure is recommended to be provided using a JSON schema. And here we have chosen the draft version 7 of the JSON schema. Here, some samples of uplink and downlink examples, how it's structured, giving the type of example, description of the example, input, and output. So this is the expected output. If I give this input to the codec, this is the expected output. This is really useful as example. The downlink encode examples, the type is already downlink encode, and the description input as a data, as we said, and output as a bytes. And these examples are not only used for successful decoding process, but also to give an idea of what are the expected output if the application server or if the decoder received a wrong payload, for example, or a crashed payload. So this is an example of an errors also. So the example is not only giving the successful ones. You see here we are giving a bytes and F port, and we get the expected output will be invalid downlink payload unknown ID. You see, so here we have we give an example of what's an error can be presented. And also some samples of how the data description must be provided. Here are two JSON schemas that describes the output of the decoded uplink and downlink. For sure, no data description for the encoded one, as the output is always an array of bytes and an F port. So you can see the decoded uplink schema. We said that we may receive as an output when decoding an uplink a temperature, a humidity, a pulse counter. These are the three possibilities. There is false, no additional properties. These are only the properties that can be sent by this device. The decoded downlink also, we have said that we can send to the device, these two types of data. Set a pulse counter threshold, set an alarm, for example, and no additional properties. So this is describing and giving more information to ease the integration on any application server. Also, there is some requirements, additional and required characteristics that must be taken into account when created any new codec following this standard specification. For example, the security. For security, we have set these are more detailed in the specification. So, for security reasons, and because the codecs are executed directly on LoRaWAN platforms, there are some limitations on what a codec developer can do inside his codec. So the codec itself should not use any external code that get dynamically used during runtime. This is for security reasons. Another requirement will be the size of the script. According to some statistics that we have been done, and as Actility is one of the vendors and solution providers that are member of LoRa Alliance, and we really use the codecs, and there is also another members. We have done some statistics, and according to memory allocation limitations, we had decided that the size of the codec script should not exceed the 64 kilobytes, and it's really enough for a codec of a device or a group of devices. Therefore, the application server vendors that must follow this, that would like to follow this specification standard should support codec scripts up to 64 kilobytes or max. The libraries we have defined, okay, some predefined libraries should be defined, but we have started with one library, and this can be improved in the future versions of this specification. We have started with the Node.js buffer with its version 12 in order to handle raw binary data. And this is really useful to avoid any large polyfills, and this also help to not increase the codec size more and more for nothing. The recommendations from the task force would be about the packaging and testing. So the packaging, we have decided we recommend to use the Node package managers, the NPM, because it's the most widely used packaging system for JavaScript code. And also, when using NPM, this approach defines a clear code layout that can be distributed, delivered independently using the developer preferred version control tool. More details about that and the best practices to use with NPM are described in the specification document also. For testing, actually the testing of the codec is really an important process. Thus, the codec developer is highly recommended to test the codec in most possible cases, as well as error cases also, not only the successful ones. So the test process of the codec is recommended to prove a minimum of 85% of test coverage. And we also recommend to use the Jest as a testing framework, as it's easy to use and it already supports the coverage statement. And to facilitate the use case testing process, the codec developer can benefit, and that's why we have said that examples are optional but important. The codec developer or the application server can benefit from the examples files by using just one normalized and already implemented JavaScript spec file in order to get all the payload examples, inputs, and the expected outputs, and thus we can do the test automatically and give the coverage of the whole test in one script. So the examples are really helpful for the application servers and for the user of the codec. That was all about the standard API. You can find a reference to the full specification if you need more details. In the resource boxes also, on your screen, you can download today's slides also. And if you find, if there is any comment, any feedback, even a clarification are welcome. So do not hesitate to reach me out, me or Alper, and here are our direct contact emails. I will hand to Megan again.
Perfect, no problem. Thank you so much for all the great information in your presentation today. As Mustafa mentioned, there is a resources box on your screen, so that will take you directly to the link that you're seeing on the screen. And there's also a link to download today's slide deck as well. If you're also interested in becoming a LoRa Alliance member and joining the LoRa Alliance ecosystem and getting some of those benefits that were mentioned today, there's also information there, a link to get more information in that resources box on how to become a LoRa Alliance member as well. As a reminder, use that Q&A box that is on your screen. If you do have any questions, we are going to go ahead and go into the question and answer session now. I do believe we're having Alper connect and join us and help moderate the Q&A. So let us get him connected. Use that Q&A box to type in any questions you have, and we're going to go ahead and get those answered right now. So just give us a moment here to regroup, and we'll start the Q&A session shortly. Thanks, everyone.
All right, great presentation, Mustafa. Thank you very much. And it seems like we have a very wide audience today, and they've already started putting their questions in the Q&A box. So if you haven't already done so, please go right ahead and type your question in the Q&A box, and here we go. All right, the first question, Mustafa, is why is there no encode uplink?
So actually, the uplink is sent from the device. It will be encoded in the device. It's sent over the air. So the only need for this uplink is to decode it on the application server, as it's already encoded by the device. So there's no need to encode the uplink again. It's already encoded.
Right. Yeah, they're already binary encoded, so there's no need to further encode them. And then the next question, well, I think it's a statement, so let me read it. Usually application servers adapt to devices in the market and integrate one by one devices needed to support. But standardizing device protocol and application APIs is the way to go for sure. So yeah, like I said, this is a statement which makes perfect sense.
I can add
yes,
something to this statement. So even if it's one by one supporting of devices, but the integration of each one in this process would be easier and faster with this standard, as the codec will be compatible with all application servers.
Yep. All right. The next question is why not both JavaScript and Python on app side and C on the end device side? Also, encode uplink seems to be missing, which we talked about. Yeah, and the last part is we already covered. So it's the question about Python.
The JavaScript and Python.
Yes.
So actually, we have decided on JavaScript, one which is more popular for this purpose among the ecosystem. But sure, in the future, when there is a demand for Python binding, we can add it to in next versions of specification. But the JavaScript was the most popular in the application server vendors.
And I think the question or the point about using C on the end device, that's not clear because the end device already knows how to process the application payload, and whatever language it's using, it can keep doing so. There's really no codec API relevance on the end device side, right?
Right.
All right. Okay. Then the next question is, does the codec ID differentiate between different versions of the same codec, or are there different codecs for different applications? I thought the whole point of the standard was to have one codec for all applications.
Actually, the codec ID would be added to the QR code as we have already mentioned in the specification in details, but will be added to the QR code as there's vendor IDs that are registered in the LoRa Alliance community. There will be codec ID. So yes, one codec can be used, one standard codec can be used for all application servers, but no need to change the ID on every version, as the codec, when you have the codec ID, maybe we can discuss it after, but maybe we have one codec ID per version, or we add to the QR code the codec ID with its version. But yes, you are right.
All right, and the next one is again about codec ID. If I have devices that are using different payload formats today, can I define multiple codecs and use multiple codec IDs?
Yes, for sure. So they can be there can be multiple codecs for one vendor. So it's not one-to-one relationship between vendor ID and codec ID.
Yeah. So a single vendor would have a vendor ID, and then they can have multiple codec IDs, and depending on the application, they can use a different codec ID, right? All right, and what about dynamic schemas? In other words, when the content of your uplinks might not always be the same structure.
I think here you are asking about the JSON schema, which is recommended to be added on the codec. And normally, if you have a dynamic JSON schema, there is an option. You can just do. There's an option of having one-off inside the schema definition. You can have one-off, and inside an array, you can put multiple schemas. So there's an option in that for that in the JSON schema.
Right. The next question is, I understand how I submit the formulas of uplink and downlink packets, but how do I actually tell the LNS, the network server, the decoder encoder code itself?
Yes, actually, normally when provisioning any device, you can link the device with the code by the codec ID. That's what was the goal of having a codec ID set on.
Right. So go ahead. Sorry, I didn't mean to interrupt.
No, that's okay.
Okay. I was going to say the user who's provisioning the end device needs to provide the codec ID to the system like an application server, so the application server knows which codec to use with the traffic or with the frames, application payloads coming from that given device. And the next one is, what is the feedback of other network server providers beside of Actility, for example, TT and Chirpstack, to implement this?
Actually, we had several contributors in this specification and this task force. One of them was, if I remember the names, Johan from TTN already. There's some from. I don't remember actually the names of companies, but yes, there's multiple LNS providers that were participating in the task force and in the specification. So we have the same. We are on the same path.
Right. So this is a LoRa Alliance standard, and it's produced by the Application Payload Codec API task force under the technical committee, and we had members from various parts of the ecosystem, not only contributing, but also approving this specification. So it's a joint work, and it's a LoRa Alliance standard. Okay, the next one is, well, thanks for presentation. Well, thank you for joining. One question, why using NPM for distribution and not a public API or repo that would allow integration at runtime and not only at build?
Actually, also, this is like the one of JavaScript. This was the most popular in the ecosystem, among the ecosystem, and also it can be, let's say, have the same structure for all the distribution. But to add to that, the NPM packaging of the codec was a recommendation by the LoRa Alliance specification. So it's not mandatory, so it can be delivered in another way, but this is a recommendation to deliver it as an NPM.
Mm-hmm. All right, and the next one is, will there be a codec repository available at the Alliance website?
Yes, actually, we have decided to have a GitHub repository for the LoRa Alliance to add the codecs or even the codecs with their IDs. That was the plan.
Okay, and is there any code example for the codec available at GitHub?
Or sorry, is there any code example? Maybe I mistake with the question because I was answering on this question. So the GitHub repository was to add the sample, the sample or the example of the codec at GitHub,
yes,
and not for saving, not a repository for saving all the codecs. But on the LoRa Alliance side, we will have the codec IDs.
Right. The alliance actually manages the vendor IDs, and the codec IDs are left to the vendors. And there would be a sample codec for others to develop, but otherwise a full repo won't be hosted, right? It'll be left to the market to build it and provide it to the rest of the ecosystem. All right. And this one you already answered. We are working on providing a code example. So the next one is using NPM would expose my decoder code to the public. What if I don't want to expose it?
What if I don't want to expose it? You can deliver it to the application server by any other to the public. Yes. So using NPM, you can also pack a code or the code and the metadata in a private one. No need to publish it on the NPM public when using the NPM package. So there's a choice to have a private one.
Right. Right. Yeah. Then you have to take care of how to deliver that to the target platform, but you can keep it away from the public eyes, yeah, if you want to. Let's see, okay. Here's the next one. It seems to be that the end device makers do not have to change anything. This payload codec is more oriented to standardize the exchange of data between the LoRa gateway and the network server. Is this correct, is the question?
No. Actually, I will repeat, I will go back to a previous slide, the example that we had presented. We see the device maker needs to develop a codec for each application server. So yes, there's an impact on the device maker. After using this API, you'll have only to decode one codec for all the servers that supports the standardization. So there is an impact on the device makers also, not the gateway and network server.
Right, but it's not the device that gets impacted, right?
Yes, not the device, but the device makers.
Yes. So device maker, if the codec is provided by the device maker, they would follow this API to provide their codec, and then if they develop their codec once according to this API, then it can run anywhere using the same API, but physical device and the software stack on the end device won't be affected. All right. Okay, so the next one is, have you defined a list of services such as temperature, humidity, etc., to homogenize the exploitation between different device makers? So this is more about the semantics, the ontology part of the story.
Yes, actually, that wasn't the scope of this version of specification. Maybe in version 2 or in another specification that will complete. But yes, this specification was needed to open the way or to open the path to start doing that, to start standardizing even as we have many standards of exposing data. As for example, for Microsoft, there is the DTDL. For Google, there's another one. We can add some standard of exposing these data, but this wasn't the scope of this task force or this specification. It may be in the next versions or in other specifications.
Right. Yeah, I mean, we chose to go step by step, and we took the first step, and what's been asked here is the next step. About standardizing how data is represented. And there are some ongoing discussions around that, but the timeline is TBD. All right, then here's the next question I'm going to go. Yeah, okay. Usually in one uplink is more data transported like temperature, pressure, and humidity. Is this covered in the uplink encoding?
I think it's more data transported like that. There's no uplink encoding. We have already answered this one. So.
Yeah, so there's decoding, but the decoding can handle decoding multiple different types of data, right? I mean, a single uplink having 3 different information elements, yes, the decoders can handle that as well. Yeah, definitely they can. Yeah, and the next question is something we just recently talked about. Is there a standard for decoder output on the horizon? Example temperature is always temperature and unit is Celsius. Yeah, that's a potential next step, and then the timeline is TBD. And obviously, just like for anything else, we would highly encourage, if there are members in this audience or if they are considering to become a member, we would highly encourage them and come and join the application payload Codec API task force to be part of the conversations towards evolving this standard. And the next one is also a comment, Python is more popular than JavaScript. So regarding the codecs, let me jump on this one as well. Among the members who have participated in development, JavaScript was more popular. If this attendee thinks that a Python binding should be provided as well, same thing, very welcome to come and join the task force. Even the adaptive level members can join the task forces. And as if and when we have demand for a Python binding, we can support it as well. Okay, what device uses the downlink decode? Isn't this an end device? If so, it's most likely written in C. Does need decoder written in C? Yeah, I think, this is the same participant. Regarding how the end device does encoding and decoding is all an implementation running on the end device. It's totally isolated from the rest of the system. What we are concerned here is how the application server encodes and decodes the payload between binary and JSON. So yes, the end device might be using C, but still the codec could be written in JavaScript because they are running on 2 distinct systems, right? The one written in C could be running on the end device, but the one written in JavaScript would be running on the application server. And yeah, I mean, there are different requirements in terms of the development language choice when it comes to running on the end device versus running on the application server side. All right, the next one is, will this be supported not only by LNS, the network server, but as well by the integrations like DataCake, Ubitos? These are the application servers, as you know, Mustafa. That's the question.
Actually, it will be only supported by the LNS. After that, it can be used. The result of this standardization can be used to easily integrate with other platforms like DataCake, Ubidots. According to but no, it's only for the LNS.
Well, I mean, actually, the binary could be like translated to JSON on the LNS or on the application server as well, right? Theoretically speaking, or in some given implementation, if the LNS keeps pushing the binary to the application server, nobody prevents anyone from running the codec on the application server as well. But if the binary to JSON translation has already been done on the LNS, then there is no need to further do this decoding on the application server. So at least in terms of our standard, one can run them on the network server or on the application server, or in fact on any platform that might be outside our architecture as well. We don't really have any constraints. That's the flexibility we have. We have only a minute left, so let me take one more.
I can take one of
yes.
32 because I think it's clarification also. Do you need to use the JSON schema, or can you just put everything in the decoding function itself? The JSON schema, as we said, there is no, for the moment, there is no standardizing of the data that must be exposed as temperature or temp or something. So the JSON schema here to describe the output, but it's not mandatory, it's optional. So you can put everything in the decoding function. But that was too easy to make it more easy for the application server if there is a JSON schema that describes the data.
All right, so we have reached the end of the hour. So let's stop here. There are a few more questions that we couldn't get to, and we can respond to them over email. Well, thank you very much, Mustafa, for this insightful presentation and the answers. And thank you, our audience, for contributing to this discussion as well. So with that, I think we can close today's session and everyone to have a great day.
Thank you all.